We'll discuss how to diagnose common conditions by analyzing noise spectrum. The table highlights the type of faults that can be detected through vibration measurements. Each fault can be identified by examining the frequency spectra and orbit shapes. We've also provided corrective actions on the right for your reference. Now, let's dive into the topic of mass imbalance. Mass imbalance in a rotor results from an uneven distribution of mass causing the rotor to vibrate. This manifests as a 1x frequency spectrum. You can address the mass imbalance by performing field or shop rotor balancing. It is essential to adhere to industry balancing standards such as ISO, API, and others. These standards detail the acceptable levels of remaining imbalance. API standards are more stringent than ISO G2.5 specifications. The primary goal is to minimize the force due to center of mass. Some turbo machines use ISO spec to define the allowable imbalance in the machine, and the parts are balanced accordingly. The acceptable imbalance can be defined based on the factors like rotor weight, machine speed, and the desired imbalance grade. This example here uses ISO G2.5 grade. For more detailed explanation of how to use ISO spec to define the imbalances, please refer to Part 6 video. Here is an example of 70 megawatt gas turbine balance plane. 3 different planes are utilized for balancing. In essence, mass is either added or removed to minimize forces due to center of mass. Part 24 video offers comprehensive guidance on rectifying imbalance. Machine can subject it to significant wear and tear over time and can experience an increasing in 1x vibration due to mass imbalance. If the vibration increases too much, parts may need replacement and field balancing may be required. Let's return to the table for a moment. Now let's explore the topic of misalignment. Misalignment between the bearings, shaft, and rotor can lead to 2x noise. Additionally, coupling or machine misalignment can also induce 2x noise. The presence of 1x is due to imbalance, but in misalignment cases, 2x can reach similar amplitude as the 1x's. The orbit shape resembles a figure 8. What is meant by orbit motion? When you measure a rotor motion using 2 sensors, the orbit shape is typically circular in the case of imbalance. However, with the misalignment, the orbit shape resembles a figure 8. Here is an example of actual measurements that exhibit this figure 8 pattern. So it is important to monitor the shaft vibration because it helps to diagnose the machine symptom before they get worse. Bentley, Nevada provides detailed instruction on sensor installation in your machine, which is crucial for understanding the machine behavior and vibration over time. Bentley, Nevada recommends using 2 vibration transducers for radial vibration measurements. These transducers should be mounted coplanar and 90 degrees apart within the 3 inches of the bearing, and this is for large compressors. The XY configuration provides comprehensive view of shaft centerline vibration and radial position within the bearing clearance. The probes should be mounted nearly perpendicular to the shaft centerline within an angular separation of 90 degrees plus minus 5 degrees. For integral geared compressor, a single probe per bearing is acceptable when the space constraints prevents the XY configuration. To protect against thrust bearing failure, it's crucial to use 2 thrust probes for redundancy. And a spare probe with an extension cable is recommended for internal mounting arrangement. The position measurements should be taken at the thrust bearing end of the machine and within the 12 inches of the thrust bearing to account for thermal expansion effects on the shafts. Mounting thrust probes directly through the thrust bearing is preferred, but when not possible, they can be engineered to observe the end of the shaft through other color within the similar proximity to the thrust bearing. Here is a vibration instrumentation diagram for centrifugal compressors. The shaft radial vibrations are measured at both left and right bearings. The axial thrust position measurements are also required at the thrust bearing location. Lastly, temperature probes are installed to monitor temperatures. A similar approach applies to axial flow compressors with shaft radial vibration measured at both left and right bearings. The axial position measurements are also crucial at the thrust bearing location. Also, temperature probes are installed to measure temperatures. For this geared compressor, there are 6 bearing supports, each equipped with displacement sensors to monitor the machine vibration, and temperature probes to monitor the machine temperatures. So we touched on sensor installation in your machine. Now let's revisit this table. Okay, let's look into the shaft bow. This bowing can cause 1x vibration and dropout of vibration around critical speeds in the body plot. As you could imagine, straightening the turbine rotors is vital for smooth and low vibration operation. The figure on the right shows the rotor runout measurements showing shaft bow. The rotor runout is measured by dial gauge. Rotor bowing, often due to localized overheating and uneven temperature changes during operation, can result in permanent metallurgical changes, yielding, residual stresses, and uncorrectable bowing. A bow shaft can cause axial opposed forces on the bearing, which can be detected in the vibration spectrum as 1x in the axial vibration. The most severe instances of enduring bowing typically result from the water entering the hot turbine, leading to cooling of a section of the rotor and potentially cause rubbing that can induce plastic deformation in a small part of the rotor. Example of the seal rubbing the rotor is shown on the right, which can slowly bend the shaft over time. From our observations, when the rotor bowing occurs and the total runout surpasses a specific threshold, rectifying the situation through balancing becomes very challenging. As a result, surpassing the critical speed renders it hard to operate the rotor, thereby preventing the turbine from functioning. So there are 2 viable options. Either replace the rotor with a new one, or rectifying the situation by straightening and rebalancing the existing rotor. To address the shaft bowing issue, it typically begins with annealing process. The purpose of annealing is to relieve residual thermomechanical stress caused by rubbing. During the annealing process, thermocouples are attached near the heated zone for precise temperature control. Figure on the right bottom shows how the temperatures is managed during the annealing process. The localized heating applied to a complete circumferential band at the rotor area. After completing the annealing process, runout is reassessed before proceeding to the hot spotting stage. In hot spotting stage, rapid heat is applied by torch, causing local plastic deformation. And cooling generates tensile stresses, internally compensating for stresses. It is important to note that effective straightening requires a local temperature above 600 degrees Celsius, ideally around 700 and plus minus 10 degrees Celsius. Note that these temperatures are reference only. But please make sure to limit the hot spotting temperature to 750 degrees Celsius to prevent austenite transformation. Also, avoid overlapping hot spots to prevent cracks. It is important to note that the applied heat induces compression in fibers, counteracting the tension stresses and straightening the shaft. Through iterative process of annealing and hot spotting, the shaft undergoes straightening, resulting in reduced mass imbalance in the rotor. After straightening the shaft, you must rebalance the shaft. Let's go back to the table here. As bearings wear out, machine tends to emit noise. The graph below illustrates the time on the x-axis and the useful life of the bearing on the y-axis. As you could see from this figure, detecting the bearing wear before failure is crucial. Typically, if you look at the vibration measurements at the machine below, vibration tends to trend upward over time. If the large vibration is due to bearing wear, typically it cannot be fixed by balancing. So it is important to monitor the vibration over time and make sure that machine does not catastrophically fail. To prevent failure, it is important to set the warning limit. And establishing initial values is crucial for setting limits such as alarms and warnings. And understanding the rate of increase in vibration is essential. When thresholds are surpassed, a comprehensive vibration analysis is conducted to pinpoint the precise issue and prescribe the maintenance solution. Here is an example of vibration severity according to ISO standards. We'll delve deeper into this ISO spec in a different video. But the table provides an idea of when to inspect the machine upon exceeding vibration thresholds. As you could imagine, the corrective action of bearing wear is to replace the bearings. Here is an example of various types of bearing wear. Some wear can be refurbished. It is important to understand what's behind the premature bearing failure and wear. Here is a list of key factors contributing premature bearing failure. The primary culprit is dirt, which causes wear damage inside the bearing. The figures on the right shows the wear damage due to dirt. In such cases, a thin babbitt surface layer can extend the bearing life. Soft bearing materials like babbitt have the advantage of embedding particles in the bearing surface. This embedded capability leads to the formation of holes or raised region around the embedded particles. Polymer-lined pads possess the ability to embed material, as evidenced by the illustration of the polymer thrust bearing with the embedded metallic particles. Let's go back to this list. The misalignment affects the premature bearing failure. If you examine bearing wear due to misalignment, the symptoms are polishing pattern on the one side or localized area of the babbitt surface, localized severe wear, high localized temperature, fatigue failure in diagonally opposed areas in top and bottom halves. The corrective actions involve realigning bearings or adopting misalignment tolerant designs. Let's look into bearing wear due to insufficient lubrication. The damage to the bearing surface often resembles the damage that results from overload. The surfaces can be wiped and the babbitts being smeared. Now let's discuss the bearing wear due to overloading. The hydrodynamic bearings relies on a thin lubrication film. An overload can lead to contact between rotating and stationary components, which results in temperature increases and potential melting. Here are the photos of bearing damage due to overloading. Overload can lead to severe damage to the bearing, as you can see from these photos. Corrective actions involve reassessing the design inputs and loads, and reducing the loads and considering higher load bearing design. So far, we covered the major causes of premature bearing failure. To prevent these issues, condition monitoring is crucial. Condition monitoring detects early degradation, focusing on bearings designed to fail before the shaft to prevent catastrophic failures. It's a powerful tool for proactively identifying the issue. API 670 specifies sensor locations, emphasizing the importance of accurate condition monitoring. Returning to damaged bearings, numerous companies can fix or refurbish them as shown in this figure. The figures are from Alloy Bearings, a company specialized in this field. Again, early detection of bearing failure can reduce downtime and save money. Okay, now let's look into the cracked shaft. Failing to detect and address the issue may result in progressive expansion of shaft cracks, and ultimately can involve a broken shaft and machine failure. Such an event incurs significant losses and have adverse consequences. As you could imagine, the presence of crack diminishes the stiffness of the shaft. The bending stiffness of the shaft is directly tied to the cross-section area. As cracks propagates along the shaft, the available cross-sectional area progressively diminishes. This causes a continuous decrease in shaft bending stiffness. This reduction in shaft stiffness amplifies its susceptibility to bending under static or dynamic load. This leads to an escalation in first harmonic vibration, 1x, as you could see from the below figure. The greater depths of the crack, the more pronounced the second harmonic, 2x, becomes. This is because crack causes asymmetry in the rotor lateral stiffness. Let's look into the rotor dynamic modeling. Here is the 63 megawatt steam turbine. The circumferential crack was found at first stage bucket. The machines with frequent start and stops are exposed to increased number of passing through the resonance and suffer from extensive heat and cooling shocks. And this can contribute to possible shaft crack. The crack was simulated by a change in rotor diameter at the location of the crack. This adjustment in the model accounts for material portion that does not contribute to stiffness. If you run the model, the rotor dynamic modeling generates rotor response plots as shown below. The first noticeable difference is the increasing in vibration amplitude, indicating that decreasing in effective damping. The second noticeable difference is the decreasing in first bending mode, indicating the decreasing in shaft stiffness. As you could imagine, if the shaft stiffness changes due to crack, the output rotor response will change with same amount of imbalance. The impact hammer test can confirm the decreasing in shaft natural frequency. For your reference, in part 14 video shows detailed steps on how to perform impact hammer test. As you could imagine, identifying the shaft crack is challenging, because it can obscure by concurrent machine issues such as imbalance, misalignment, or bearing looseness. But if there is an indication of shaft stiffness reduction, you could look into the possibility of shaft crack. Many research papers delve into the topic of cracked shafts and their impact on machine vibration. For a more in-depth exploration, you can find the reference at the bottom. There are two primary types of looseness, structural looseness and bearing looseness. Let's look into the structural looseness first. Structural looseness manifests when the machine lacks proper support in its base. Poor mounting, poor base support, distorted base can contribute to structural looseness. Of course, the primary cause of major issues often stems from loose bolts. The structural looseness can result in elevated vibration at frequencies such as 1x, 2x, 3x, and beyond. Indeed, it is crucial to examine the structural looseness when there is a noticeable upward trend in the frequency spectrum over time. So, conducting a thorough inspection of the base bolts is essential. The structural looseness can manifest in various ways, including examples such as broken anchor bolts. Also, the absence of grout under the frame can lead to structural looseness. And the thinness of the washer may pose a risk of deformation or yield, potentially resulting in structural looseness. Also, bolt and frame fretting, along with the corrosion-induced issues, can contribute to structural looseness. Let's return to this figure. Now, let's delve into bearing looseness or rotating looseness. Bearing looseness or rotational looseness can generate high order frequencies, including 1x, 2x, 3x, and beyond. This multi-frequency stems from a rattling motion. Excessive clearance can lead to contact between mating surfaces, resulting in a chopped or truncated waveform that serves as an indication of such contact. For example, the truncated signals in time domain indicates the contact. By using FFT, the truncated signals in the time domain is translated as the harmonic frequencies in the frequency domain. The truncated waveform is represented by harmonics such as 1x, 2x, 3x, 4x, and so on. So returning to this slide, if your machine vibration measurements displays multiple harmonics, 1x, 2x, 3x, and so on, in the frequency spectrum, it indicates the presence of the rattling motion within the machine. Additional information related to how to define the bearing fit can be found in Part 12 video. Certainly, it is crucial to monitor the overall noise level. Typically, vibration measurements can be segmented into multiple layers, each corresponding to severity of vibration, offering guidance for inspection, repair, and maintenance activities of the machine. So the crucial question is, where should I attach the sensors? Here is an example of a machine layout, and the optimal location for attaching the sensors are highlighted below. These are the prime spots for effectively detecting the bearing conditions. These spots are chosen because they facilitate the transfer of bearing vibrations, which leads to better detection of bearing conditions as illustrated here. In case of complex machine arrangement, conducting modal analysis can be beneficial for assessing the natural frequencies of the machine setup. The modal analysis provides insights into whether the foundation is weak or stiff based on the understanding of natural frequencies. Various approaches can be employed to stabilize the foundation and mitigate the vibration from the external sources as shown in the photo. Now let's look into thermal instability. Morton effect is thermally induced rotor instability. Most commonly appear in rotating shaft with large overhung masses and supported by fluid-filled bearings. The figure on the bottom shows the 1x vibration amplitude versus time. The machine speed is maintained at a constant level until the amplitude exceeds 7 mils peak to peak, at which point a shutdown is triggered. If you notice a sudden rise in synchronous vibration along with the consistent change in phase and there is no sign of rubbing, it's probably due to the Morton effect. Please be aware that it required over 2.5 hours of machine operation for significant amplitude motion to appear. So why is this happening? Let's look into this schematics. Initially, there is no temperature difference across the journal circumference of the rotor. Because of mechanical imbalance or residual rotor deflection, the high spot, which typically exhibits the lowest film thickness during the one orbit, typically undergoes greater oil viscosity shearing compared to other positions around the journal circumference. This non-uniform viscous shearing results in uneven heating of the rotor, leading to temperature variations across the journal circumference. The temperature difference within the rotor induces thermal bowing in the shaft. In cases where the shaft includes significant overhung reel or coupling, this thermal bowing can result in substantial imbalance. This illustrates thermal bowing, which can lead to substantial deflection at the overhung location. Going back to 1x vibration versus time plot here on the right, the Morton effect can cause substantial increasing in the 1x vibration amplitude due to thermal bowing, while the machine rotating speed held constant. Here's another graph illustrating how the Morton effect results in a divergent spiral vibration. It has been observed that as high-speed overhung rotor design become more prevalent, occurrence of Morton effect has also increased. The Morton effect is generally presented in all journal bearings to some degree, but usually does not affect rotors without a significant overhung masses. So how can we solve this problem? Adjusting bearing oil inlet temperature or flow rate can alleviate thermal bowing. Also, you could redesign the shaft to change the critical speed. And using a thermal barrier sleeve on a shaft within the bearing can reduce the thermal bowing. If you have any questions or if there's anything else you'd like to explore, feel free to leave comments below. Thanks for watching, and I'll see you in the next videos.